Dear students, welcome to the problem solving session on Milne Thomson's method part 7. In the two previous videos, we learned how to solve if the problem comes in linear combination of AU plus BV with some phi of x comma y. And in this session, we are going to solve few more problems for your confidence. Before going into the problem, let us have a quick recap. If f of z is analytic, suppose we take any real constants a and b, then a plus ib into f of z is also analytic. The reason is constant functions are analytic everywhere. Product of two analytic functions is always analytic. Therefore, a plus ib into f of z is also analytic, and we take this as capital F of z and we proceed the problem. Here given u minus v is equal to e power x into cos y minus sin y, we have to find the analytic function f of z is equal to u plus iv. So in the previous video, I have already said the trick. Always make your given question as real part. So I will write u minus v, then plus I into interchange u and v alone. Here we have minus, let us put plus. And then in the left hand side f of z is, the question is u minus v and the coefficient of u is 1 and v is 1 and the sign is negative, so I put positive here. So 1 plus I into f of z is equal to u minus v plus I into u plus v. This u minus v is the real part. That means my given question u minus v is the real part of 1 plus I into f of z. Here we can see the detailed step how we get it. Therefore, I am going to assume this 1 plus I into f of z as capital F of z. On the right hand side, small u minus v is capital U, small u plus v is capital V. Therefore, capital F of z is 1 plus I into small f of z. Capital U is u minus v. Capital V is u plus v. So, my given question is capital U is equal to u minus v is equal to e power x cos y minus sin y. So now we change the problem in terms of capital F of z. After this, we have to proceed as usual. Step 2, we have to take the capital U and you have to differentiate partially with respect to x. When we differentiate partially with respect to x, e power x differentiation is e power x cos y minus sin y. They don't have x and they are multiplied with e power x, so they remains same. Next, differentiate u partially with respect to y. E power x is constant, cos y differentiation is minus sin y and minus sin y differentiation is cos y. Next we have to replace x by z, y by 0. So capital Ux of z comma 0 is e power z. We know that cos 0 is 1, sin 0 is 0. Therefore, 1 minus 0. Next, uy of z comma 0, that is e power z, sin 0 is 0, cos 0 is 1. So we get e power z and minus e power z. Next, step 3. While you write step 3, you should be very careful because we are using the notation capital U. So capital F dash of z is capital Ux of x comma y minus I into capital Uy of x comma y. By Milne Thomson's method, this is equal to Ux of z comma 0 minus I into Uy of z comma 0. Now, capital F dash of z is e power z minus I into e power minus z. Now I will take this e power z in common, minus into minus plus, so we get 1 plus I. This is my capital F dash of z. Next we have to integrate this capital F dash of z, integral 1 plus I into e power z dz. I can take this 1 plus I out, integral e power z dz. So integration of e power z is simply e power z. So my answer is 1 plus I into e power z. As I said earlier, many students will do the error by stopping the problem here. Capital F of z is not my solution. I want to find the analytic function small f of z. In step 1, we found the relation capital F of z is equal to 1 plus I into small f of z. If we substitute here, we get 1 plus I into small f of z is equal to 1 plus I into e power z plus c. Now we have to divide by 1 plus I. So f of z is equal to 1 plus I divided by 1 plus I e power z plus c by 1 plus I. Now I can cancel this 1 plus I. Therefore, my f of z is e power z. Since c is constant, 1 plus I is constant. C divided by 1 plus I is another constant c1. We can keep like that. Therefore, my f of z is simply e power z plus c1. Hope you understand, students. Next, suppose for more clarity, I am taking the same problem, but my left hand side is simply 2u plus 3v is equal to e power x into cos y minus sin y. Now how to write f of z is well known to you. Just write f of z. See the coefficients of u and v. It is 2 and 3. So I will write 2 minus 3i. And then when you do this technique, always my question will be the real part. So I will write 2u plus 3v as usual, and then I have to interchange u and v. Constants remain same. So 2v 3u. Here I have positive sign, so I have to make this as negative. Done. And we are going to assume this as capital F of Z is equal to capital U plus I into capital V. You can see the procedure. Therefore, capital F of Z is 2 minus 3i, small f of Z. U is 2u plus 3v. Capital V is 2v minus 3u. After this, nothing, because we are going to assume this u as 2u plus 3v, and this problem just now we solved. So we write u, ux, uy, replacing x by z and y by 0, we get e power z and minus e power z. Next, by Milne Thomson's method, capital F dash of z is equal to ux of z comma 0 minus I into uy of z comma 0. Integrating this, we get f of z is equal to 1 plus I into e power z plus c. Now, we have to find my analytic function small f of z. We know that capital F of z is 2 minus 3i times small f of z. Let us substitute this. Now divide the equation by 2 minus 3i. We get f of z is equal to 1 plus I divided by 2 minus 3i e power z plus c by 2 minus 3i. It is not necessary to write c by 2 minus 3i. Directly you can write it as c1. For your understanding, I just do it. Now we cannot keep the complex number in the denominator, so we can simplify this f of z by multiplying and dividing by 2 plus 3i. So 1 plus I divided by 2 minus 3i. So we know that a plus ib into a minus ib is a square plus b square. So we get 2 square plus 3 square e power z plus c1. Now we have to simplify the numerator. 2 plus 3i plus 2i. I into I square, we get minus 3. Therefore, my small f of z is minus 1 plus 5i divided by 13. 9 plus 4, 13 e power z plus c1. The difference between this problem and the previous problem is only the left hand side changes. So accordingly, we see the different complex constant. Hope you understand, students.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.